Differential equations, we are looking at our last review assignment of the semester, the 4.4, 4.7 e-learning review. We're going to start off with 3 Cauchy-Euler differential equations. And of course, as you're looking at this, a Cauchy-Euler differential equation, guys, is always going to work with the assumption that y equals x to the m is a solution. And what's really nice about that, you don't have to show all the details for this, but here you'd have an a is equal to 3, b is equal to 6, c is equal to 1, much the same way that you would find coefficients in a quadratic. What you're going to see is if you made that assumption of y equals x to the m being a solution, and if you were to take derivatives, substitute that in, and really just do some work dividing things out, you would eventually come to this basic equation of am squared plus b minus am plus c. In other words, you would now have this quadratic right here that you could now solve. So you'd have 3m squared plus a 3m plus 1 is equal to 0. And right now you could use the quadratic formula. The quadratic formula, as you'd solve this quadratic equation, would yield the following. You'd see that m would equal, you could see that you would get opposite of b, so that would be opposite of 3. Now we're calling this like our b, right? So we'd say plus or minus b squared, that would be a 9, minus 4 times 3 times a 1, all over 2 times 3, which is a 6. And m would equal negative 3 plus or minus, well, 9 minus 12 is going to be negative 3. So I'm going to pull out that I right here. And this would be m equaling, well, negative 3 over 6, you'd get negative 1/2. And then you'd have an I radical 3 all over 6. So what we're seeing is, when you get these complex solutions, what we saw is that your general solution, and we're just remembering what we saw prior, and this is what we saw in our video in our notes the other day. You could see this would be our general solution. Well, how is that going to lead us to where we're going? Well, this will be x to the negative 1/2. Here's a c1 cosine of, well, we'd have a radical 3 over 6 natural log of x plus a c2 sine of radical 3 over 6, here we go yet again, times the ln of x, and there you have it. So this might be the messiest form of an answer that you're going to have for these Cauchy-Eulers. You can see that you're going to start off with this am squared plus b minus am plus c. That's going to lead you to a quadratic. You just solve your quadratic as you always do. And what you are going to wind up with, at least in this regard, is the answer that we just came up with. You would naturally expect to see complex solutions in a Cauchy-Euler. Again, let's keep going, though. Let's see what we're going to have for number 2. We can assume that y equals x to the m is a solution right here. And our a would equal 1, our b would equal 10, our c would equal 8. And of course, we're going to have an am squared plus b minus am plus a c. And, this is going to be a 1m squared. Well, what's 10 minus 1? Well, that's going to be a 9. And then we just have a plus 8. This thing's going to factor pretty fast to an m plus 8, m plus 1 equals 0. And using your zero factor theorem, it's only going to take you a moment to see that you'd get m equals negative 8 and m equals negative 1. And that's going to lead you then to having an answer of x to the negative 8. Have some general constant in front of that. Have a second constant. We'll have x to the negative 1. So that works out rather nicely, and we're going to be able to get our solution quickly. Well, let's jump over to number 3, our last Cauchy-Euler. We'll stop the video after this one. Very, very, very similar kind of a setup. We're going to assume that y equals x to the m is a solution. And, here your a is equal to 1, your b is equal to negative 3, your c is equal to 4. And again, thank goodness you don't have to go through the derivation that we did in that video. You're more than welcome to do it. If we had negative 3 minus 1, you could see here we'd get a minus 4m. And here, no big surprise, you can get finally what we would call double roots. Your factors are, in other words, identical. So we'd have m minus 2 and m minus 2. So you'd get m equals 2, m equals 2. So where are we going with the solution? Well, we, of course, are going to have a c1, a constant, times x to the second. That's what we're assuming here. But what you're going to see is with this duplicate root for Cauchy-Eulers, we're going to put in a factor of the natural log of x there, an ln of x times x squared. And really, that wraps up our first part of our review, the first 3 problems, the Cauchy-Euler differential equations.